Now that we have a lot of the theory behind linear regression behind ourselves in the previous two parts, we're going to spend some time and do some examples in MATLAB that will hopefully kind of emphasize why we do these things and how we can do it inside a programming language. The first thing that I do when I'm coding up in MATLAB is always start with a CLC command. If you recall, that command clears the command window. I usually clear everything. So I clear all, that's going to clear my workspace. So this thing right here, which has some stuff in it already. So I'm going to clear that. And then I'm also going to close all, effectively closing all the different figures. All right, well, if I have some data points, I'm going to have them in two different vectors. The first vector is going to be in X, and we've seen before how we can make a vector in X. So I open it up this way, and then I'm going to have 4 data points. One of them has an X value of 1, one of them at 2, one of them at 5, and one at 4. Okay, and just to kind of remind everyone about how we enter in data, if I hit F9 while highlighting it, oops, I gotta copy and paste this over here. All right, I have a column vector in X. Down here you can see in my command window. Let's scoot this up this little bit here for a while. And as a result then, because I have these semicolons, I know that I'm going to have a column vector. If I check my workspace back here, okay, I have a whole bunch of other stuff that I need to work on, but at least in this X, all right, I have the 1, 2, 5, 4, and I haven't run this in this mode, so let me just run it here. When I go back to my workspace, it's going to be empty because I ran those 3 different lines of code. All right, so now I've got my X, and of course it's going to be a column vector because I separated it with semicolons. Okay, and this means a new row, a new row, a new row, and of course at the very end I don't need a new one. If I put a little semicolon right here, I'm going to suppress the output. All right, well here's my X, and I need Y's, so I'm going to make a copy right there. And I'm going to dial in some numbers. Let's say I do, I don't know, let's say 9, 4, I don't know, 1, and 3. All right, so now I've got my X, I've got my Y. Let me just run it here again. And sure enough, now I've got my X and my Y inside my workspace. I'm not showing X again in the command window because I've suppressed it with a semicolon at the end of the line. In my workspace, I've got X and Y. All right, well, now that I've got my data, it'd be good if I could start to plot it just to take a look at it. So I'm going to do figure 1, and then I'm going to plot X versus Y. Come back here, run it again, and here's my first plot, and we'll notice then that it's not monotonically decreasing, and in fact there's a line connecting these points. However, since this is raw data, it doesn't make sense for me to link it together because I might have some points that happen before other points. And in fact, if I look at the order right here, I've got 1, 9, 2, 4, 5, 1, and then 4, 3. X is not sorted, and neither is Y, because they're just random data points. So it'd be better if I actually change this not to a line, which is the default setting, but to different points. So I'll come in here and I'll do red circles. Okay, and I'll try it again. All right, and now you can see I've got 4 red circles, I've got 4 red data points, and generally speaking, we can kind of see that there's like a downward trend from left to right if our X on this axis and our Y is on this axis. Now we should probably remind ourselves what are the labels, and so in the plotting function, or rather within the figure, we can add an X label and a Y label, and we'll plot it again. And now we've got some labeling here, and I don't like this point right on the corner. It's hard to kind of see. So what I'm going to do is I'm going to open it up a little bit and actually have an axis that sets this from 0 to 6, and this one from 0 to 10. And the way we do that is also with a function, axis. Okay, and if we want to take a look at whatever these different functions mean, we can always come in here and type in help axis. It's going to come up with a whole bunch of things that we can do to the axis, and the first one is the one that we're going to focus on, and so it goes from y min to y max. That's good. I wanted to go from 0 to 6, and then from y min to y max is 0 to 10. All right, make sure you follow the syntax because there's going to be a vector. In this case, it's going to be a row vector inside the axis function. All right, we'll hit run there. We'll see if it pops up, and sure enough, now I've got my 4 data points. They look really nice, and I'm ready to go off and put a best fit line into this chart right here. All right, so let's go back to our notes here again. And I'm going to go up just a slide or two. Let's go to this one right here. And effectively, I want to make a line, and so if I want to make a line, I need 2 parameters, a1 and a0, and I can use this equation to extract out the values of a1 and a0. All right, so let's go off and calculate a1, which is the slope for that best fit line, and we're going to multiply n times some sort of summation, but we need to define n, so right before I'm going to define n as equal to the length of our x vector. And sure enough, this line right here is going to give us the number of data points that we have. So now that n is the number of data points times, well, summation. How do we do summations? We can do help. Let's do summation. And summation is not found, so let's try something else that is often used for summation is sum. And sum of x is perfect because it's the sum of all the elements of a vector x, which is exactly what we have. We have sum of x times y. But x times y is going to be problematic because they're not conformable. Okay, let's just copy and paste it down here and then do this. Okay, so we can't multiply 2 column vectors together. We have to have it element by element, which means we need a little dot inside of it. And so now we can check our sum. Actually, let's just do x dot times y. Sure enough, it's 9, 8, 5, 12, 9, 8, 5, 12. And then the summation of those would be 9 plus 8 plus 5 plus 12 is 34. All right, so now we can go off and we can write the rest of this. We'll do sum of x, in this case, times sum of y. And all of that is going to be in a numerator, so I need to put parentheses around it, and then divide that by the denominator, also in parentheses. And it's very similar. In fact, it's going to be n times sum of not x times y, but x times x, okay, or I could do it x squared, minus sum of x, okay, to the power of 2. And of course, this right here is going to be just the values of 1 plus 2 plus 5 plus 4, which is 12 squared, 144. Just give a little check right there, and sure enough, it's correct. Whereas sum of this one, okay, let's give it a check, it's going to be 1 squared plus 2 squared plus 5 squared plus 4 squared, which is 46. All right, so now we've got our a1 right here. We now need to do our a0. Okay, and our a0 is a function of a1. It uses y bar, but y bar is nothing more than the mean of y. Okay, and if you're unsure about what this mean means, well, then we can go off help mean in our command window, and sure enough, the average or the mean value with this function of mean x is the mean value of the elements in a vector x. All right, so we want the mean value of y minus a1 times over here x bar, or the mean value of x. All right, now that we've got our a1 and a0 parameters based upon this formula, we need to go off and draw a line on top of our figure to see how good that line is in representing the data. So in that case, we need some sort of x line. Okay, and we'll go from 0 all the way up to the other end of our extreme, 6, right here. We have y line, which is going to be then a function of x line. It's going to be, well, a0 plus a1 times x line. Okay. So now we have our, excuse me, our line. Now we need to hold on, which effectively says that I can keep my data with this plot and then have another plot command, which will then do x line and y line. And in this case, I'm going to make it be a blue line. And let's see how we do. All right, here we go. We've got our 4 data points, and we can see that sure enough, we do have, okay, a0, which is the intercept point, and it was calculated to be 9.35, and we have a slope that's negative, and the slope is this a1 value, okay, and it goes from that 9.35 all the way down to somewhere between 5 and 6 when it crosses the x-axis. Okay, so what happens then if we add another data point? Well, let's go back up and we'll add another point somewhere about right here. Let's add 5, 5, 7. So come in here and I'll add 5 and 7, okay, to my x and my y vector respectively. And now since I've got this program, all I need to do is hit run, and I'll be able to see how it changes. In this particular case, the best fit line is going to be slightly less shallow in the sense that it's still going to be negative, but the slope is going to be minus 0.9545, okay, because this point is pulling it up a little bit on this side, and the intercept is a little bit lower, somewhere around 8. Well, what might be nice is for us to try to figure out what the sort of quality or error in this line representing the data is, and we use, if you recall from the previous part, this idea of the r squared value. Okay, and it's composed of two values in a ratio, st minus sr over st, and st and sr were defined on the previous slide, where sr is the sum of squares of the residuals, and st is the sum of squares not of the residuals, but of the residuals with respect to the mean of the data, or the horizontal line. So let's go off and we'll spend some time figuring out what the r squared value is for these particular lines. We'll start off by doing SR, okay, and SR is the sum of a couple of things. It's the sum of all the data points, and so that's y, minus, well, the model. Well, what is the model? Well, the model is actually this thing right here, okay? So I'm going to plug it back in, and you can notice that there's a negative sign right here in front of it, which of course, if you propagate throughout the model, it would be both the negative sign in each one of these. Except it's not that we want the summation of the line, we want of the actual data itself, to see how well the data is away from that line. Okay, and now we need to take this whole quantity right here, so I'm going to put another set of parentheses, and I need to square that, and since it is a vector, I need to make sure that I square each one of the elements, and so I need to do a dot right there. Okay, same thing now with st. This is almost identical, except the model is degenerate in the sense that it's not necessarily this model right here, okay, but it's going to be the mean value of y. Okay, the same sort of thing. We need to square it, we need to sum it up, and then we have all the components for our r squared value. Okay, so r squared value on the next slide is st minus sr. So st minus sr, all divided by st. But of course, don't forget that we need to have the parentheses for the numerator so that it makes the right equation here. All right, so now we're ready to kind of analyze the goodness of fit, or rather the correlation coefficient of how well this particular line fits the data. I'll hit run again. We can see that now I've got my x line, my y line, my SR is 28, my ST is 40. Okay, and so the r squared value is 0.2948. Okay, so there's some error there, because if the r squared value was at 1, it'd be a perfect fit, and if r squared value was at 0, this would be a perfectly horizontal line. Let's go back and we'll remove this point, and let's see if in fact the process of performing linear regression can do a better job of matching the other 4 data points. So I'm going to now take off that last point. I'll just hit run. The figure looks a little bit tighter, and as a result, the r squared value is in fact better, 0.8317. Again, it's a goodness of fit metric. It kind of shows how close the data is to the best fit line. All right, well, this is great, but what happens though if I have some sort of point way up here? Let's put it at 711. So I'm going to come in here and I'll do 7 and 11. Okay, I'll rerun it here real quick. Okay, we can't see that point, so I'm going to go off and change the axis to go from 0 to 10 and 0 to 10. Okay, and I still can't see the point, so I'm going to go from 0 to 12. All right, in this particular case, I've got 1, 2, 3, 4, 5 data points. I've done the exact same process before, but now my r squared value is very close to 0. In fact, it doesn't do much better than just a horizontal line, which would of course be that mean value of all these different data points. Okay? So as a result, it seems that my first order model is insufficient of doing a really good job of feeding this data. And in fact, the way I'm moving the mouse right now is indicative of the fact that a second order model might be a little bit better at matching all this data. So let's go off and do the same sort of thing, but in this particular case, we're going to try to find A0, A1, and A2, the three parameters for a quadratic fit, or a second order polynomial. Well, for that, we need to have this slide right here, okay? And we need to do the first derivative of each one of the values of interest, A0, A1, A2, and set those equal to 0, and it's equivalent to 3 equations and 3 unknowns. And at the end of the day, we can make a matrix that looks like this, and using matrix math, solve for the unknown vector, or the A0, A1, and A2 parameters. So let's make our big A matrix, okay? And based upon the formula on slide 16 of the presentation, we see that the first element in the first row is going to be the length of the vector, which of course is the number of data points. We know what the second element is. It's the sum of all the x's. And the third element in that first row is the sum of all the x's squared. And of course, since x is a vector, we need to make sure that we dot it so it goes element by element. We move on to the next row, and it's going to be sum of x. And then, based upon the formula, it'll be the sum of x squared, and then sum of x cubed. All right, hopefully you can see the pattern now. But now we can move quickly to the third row and just remove that first element, and then copy the second to last element, and then increase its power so that we have sum of x to the fourth down right here. And as easy as that, we've got then the A matrix, or the coefficient matrix, that represents all the coefficients inside these three equations with the three unknowns. Let's just copy and paste it down here and take a look at its form. All right. Let's do the b-side vector now. The b-side vector has only one element in each one of its rows. The first one is the sum of all the y's. Okay, we can see that right here. Then we need to do a semicolon because we want to move to the next row. It's going to be the sum of all the x's times the y's. Okay, and again, we need to do element by element, so we include a little dot in front of the multiplication sign. And then the very last one is the same sort of thing, except that we do x to the power of 2, okay, and we also need to do a little dot product right there because we want to do element by element of x and multiplied by element times the y. Close off that column vector, let's give it a check, and there's our b-side vector. All right, well, now that we've got a matrix vector problem, we can solve for little a, and I'll have little a be A0, A1, and A2. This is going to be equal to the inverse of A. Here's one way that we can do it, times the right-hand side vector. And of course, the inverse of A needs to be on the left-hand side of the vector so that these two matrices, or rather vectors, can be multiplied together. All right, so I'll just pop those all in here again, and it looks like we get A values of 15, -7, and 0. Okay, note that these are little a, so these are going to be the parameters inside our quadratic equation. All right, well, like it was above, we can copy this over, but in this case, I'm going to call it x line 2 for second order, x line 2 for second order, and y line 2 second order, except now we can't use A0 and A1 because those were the parameters with the previous problem. We need to change it into A1, which is going to be this guy right here. We need to have A2, which is this one right here, and then we need A3, which is the third element right here, and that's going to be the coefficient in front of x line squared. Okay, don't forget the dot again, because x line 2 is actually a row vector, and therefore we need to do element by element. All right, and also we need to go and change what the values are in the next plot line, and I'm going to make it into a green dash dash line. Okay, then we'll hit run. We'll see how we're doing. We're doing pretty good, except now we need to extend our x vector. So I'm going to extend both of our vectors out to, say, 10. There, 10. And there, 10. You run it. All right, and so we're doing a much better job, it appears, in terms of hitting the data and minimizing the residuals between, again, the data itself and the best fit line. In this case, it's a best fit quadratic line, or best fit line of polynomial degree 2. It looks a little bit coarse down here, so why don't we go and increase the resolution a little bit by putting in some sort of stepper of 0.1. I'll rerun it right here. All right, and now it looks a lot smoother based upon the resolution of our screen and so on and so forth. And we're doing a little bit better in terms of, like I said before, minimizing the residuals. All right, well, we've got some data that's showing up, so I'm going to suppress some things. Right here and here, and right here and right here. I'll hit run again. Okay, now we've got our A matrix, our B, and our A, so I can suppress those now by putting some semicolons right here. I'll run it one more time. All right, and now we can see that our r-squared value is 0.01 for the blue line, but we don't have an r-squared value for the green line. So now we're going to go off and we're going to copy this little section right here and pop it down here. And now we're going to calculate, well, the r-squared value for the degree 2 line. But we need to change all these things because now this model right here is not the right model. We have a much better model. In fact, this is our model. So I'm going to take it and pop it into right here. Except again, it's not the x line 2 that we're worried about. We're actually worried about those specific points. So we'll change x line 2 to be the x's. Okay, and now SR, I'm going to call it degree 2. Okay, it's going to give the sum of squares of the residuals for the second order polynomial. Okay, using the difference between the model and the data at those data points, all squared and all summed. Okay. Same sort of thing right here. I could call this degree 2, okay, and change it. But over here on this side, the model is going to be the same. So in fact, I can just suppress this and use the old ST, but I do need to change the SR to be the degree 2 SR. All right, now we're ready to go. I'll hit run. And now we can take a look at both the figure, the data points, the two lines, and the two r-squared values. In this particular case, the r-squared value for the degree 2 polynomial is going to be 0.92. It does a really good job. It's almost at 1. And the r-squared value for the first polynomial is terrible. It's almost at 0 because it's nothing more than almost a horizontal line. So as a result, the r-squared value can kind of tell you how good your fit is. Okay, and it might indicate that you need to increase the polynomial, but you need to be careful about increasing it too far. In the sense that if you have a polynomial of too high of an order, it may be that you start to overfit. The last thing that I want to talk about is that if we had 2 points with a second order polynomial, we would only actually have 2 equations. As a result then, we wouldn't be able to fit it so well, so I'm going to finish that up with this example by taking just these 2, and I'm going to take away the last 3 points. I'm going to suppress these 2, and so now I've got 2 data points. I'm going to hit run, we'll see what happens. Well, we know that the first order polynomial does a good job, and in fact it's going to do a perfect job to the point where the r-squared value is actually 1, right here and right here. Okay, but you'll notice then the lack of a green dash line for our second order polynomial. Because why is that? Well, the matrix is close to singular or badly scaled. Okay, effectively we don't have enough data points to extract out 3 equations, which means we are unable to figure out the 3 unknowns, A0, A1, and A2. And as a result, there's going to be an infinite number of second order polynomials that can cut through 2 different points. And we'll talk about that a little bit later in the next part of this lecture.